All right, we are back to wrap up chapter 8. We had started the tautology checker last time, and we were pretty close to wrapping it up. Um, and then there is another small example, which is the abstract machine. Okay, uh, so let's review what happened in the tautology checker last time. Uh, there you go. These are the type of propositional logic formulas we are interested in verifying whether they are a tautology or not. Tautology means that they are always true. Okay. So, for example, the formula A and not A, that would be always false, right? Because A and not A cannot be true at the same simultaneously. So that is certainly not a tautology, and so on. Okay. So the idea is to try to generate all possible values for the variables in these formulas. Okay, and these all possible values, these are referred to as substitutions, or sometimes in the math world they're referred to as interpretations. Okay, so for example, if you had two variables a and b, there would be four possible substitutions you can make for a and b: true, 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 false, false, true, and false, false, right? So those are each one of those substitutions values for a's and b's is referred to as a substitution in this project, and in the traditional mathematics, it's referred to as an interpretation. Okay. Anyway, or another way to look at it, that each of those substitutions is a row in the truth tables, which you studied in discrete math. Okay. And syntax for this propositional formulas is defined here. We allow not, and implies. Those are the three connectives we allow on propositional formulas. So you can see that this is a data declaration called data prop equals, and then there are five possibilities there. Three of them are the general recursive parts here: the not, and imply. Okay, and the first two are the const, and we will use the Haskell Boolean itself, true and false, and var with a single letter, I guess, char, to denote the variables like a, b, and so on. Okay, so those are the five, and we saw these some examples of actually the same four examples up here, coded in this format using the prop data type. Okay, so prop is a new data type which represents a propositional formula, and these are all the values constructed out of the rules. So these look very much like grammars to you. Okay, all right. Then we talked about the given a substitution, which is an associative array like that, a key value pair. Key would be the variable, and value would be Boolean, true or false. Okay, so here you go, associative key and value. Okay, key is a char and value is a bool. And this associative array we have seen before, so I'm going to skip that quickly. And we had a eval function which takes a substitution such as this here: a gets a value false and b gets a value true, and so on. Okay, values for each variable, and a formula, proposition formula, which is something like this. Okay, which is actually a value of the type prop. And what this eval does is it returns a Boolean value, true or false, which is the final value for the proposition based on the substitution. Okay, which is basically the answer on the truth table on the rightmost column. Okay, all right, and it's pretty straightforward. It's a recursive definition. If you have a constant b as the prop, then b is the answer, right? Because constant true is the answer, and constant false will be the answer. Okay, and if we had a substitution s and var variable x, okay, then the answer is whatever x is in the substitution. Okay, so you go and find, so that's the find operator here, which will go find, assuming it's available. Okay, so we will not have a situation where it's not available. Okay, and then for the not and an imply, these are the standard definitions. Okay, I'm going to skip, I think we did that. And then we can, given a substitution a false, b true, and given p2, which is one of the earlier formulas, it evaluates to true, and p3 evaluates to false. Okay, so that is the easy part. Then we started looking at, because our main goal is to verify if a formula is a tautology or not. Okay, and the only way to verify this is to generate all possible substitutions and verify in each substitution whether the formula is true, right? And if it is true in each substitution, then it means that it is a tautology. Okay, so that's why we have to have an ability to generate substitutions, and that's a challenge. Not a challenge. I mean, by hand we can do it easily. Uh, uh, but it is exponential in size, right? We all know that the number of rows in a truth table is equal to 2 to the power n, where n is the number of variables, a, b, c, and so on, right? So it's a computationally time-consuming task of finding all substitutions given n variables. Now, of course, if n is small, like 2, 3, 4, 5, that comes out pretty quickly, okay? And our examples will have only 2, 3, 4 small examples of few variables, okay? But in general, this number of substitutions can be 2 to the power n. Not can be, will be, okay? Will be 2 to the power n. All right, so what we're going to do is we're going to write some code to generate the substitutions, okay? Now, the first thing, obviously, to find out is what are the different variables, right, in the formula itself. Go and determine what are the unique variables in the formula, because for each variable, we'd have two possibilities, and that's how you get the 2 to the power n, and that's what this function does. What this function does, vars, is takes the prop, which is a formula, a value, which corresponds to the formula, value of prop, okay, and returns a list of characters which will contain I guess in this case it will contain even the duplicates, and we'll have a way to get rid of duplicates later. So it just accumulates all the characters, all the variables in the formula, okay, into a list, okay. And again, the definition is very intuitive and recursive, just like the eval, okay, constant underscore. If it's a constant, there's no variable there, so you have the empty list. If it's a var x, then that is the variable x, so you have list x. Not p would be all the variables in p, okay. We are not interested in the meaning of not at this point, because we're just collecting the variables. And similarly for the p and implies pq, it'll be all the variables in p plus all the variables in q. Okay, that's a pretty straightforward, simple variables. And you can see that when you do vars on p1, p2, p3, p4, the four formulas, you get AA, ABA, AAB, AABB. Okay, now there are duplicates, obviously, and we'll get rid of them soon. Okay. Now we are ready to generate all, and I think we had completed this version of the bools1 function. What this function does is that it takes an integer, okay, we'll see why, okay, in a minute, okay. It's yeah, maybe it's a good idea to see what those integers are. What we're going to do is you know that each of those substitutions technically correspond, because there are 2 to the power n possible substitutions. If you look at the binary version of the integers between 0 and 2 to the power n, okay, let's take 5, okay. When you take 5 and when we convert the number 5 into Boolean, it'll be 101, and when you translate a 1 to a true and 0 to a false, then you'd get one substitution there, okay. You'd get true, false, true for the 5, okay. And that's how we are going to generate, okay, because we know there are exactly 2 to the power n possible substitutions, and those substitutions can be derived from the numbers 0 up to 2 to the power n minus 1, okay, by converting into bin binary, and then translating each letter, or excuse me, each bit to a true or a false, depending on 0 and 1, okay. So that's what this bools1 does. It's pretty straightforward, okay. Bit is, we'll assume that that's a type, bit equals int, and int to bin, I think we have seen this, and pretty straightforward. It takes an integer and returns the binary version of that, okay. And I think it produces in the reverse order, okay, because we are consing the mod 2 in front of the recursive call there, okay. So as we are getting the rightmost bit with the mod 2, okay, we are adding it to the front. Oh, actually it comes in the right order, I guess so, okay. So, let's take 6, let's say 110, right? 6 is 110. So when you take 6 and mod 2, you'd get a 0, and you'll put it in front of an empty list to begin with, right? And then you get the 1 the next time, okay? And that will go in the front of the 0, and then the 1 will go in front of the 0. Oh, I guess you'll get in the right order, okay? We can even verify this quickly. Okay, let me create a new cell here. Int to bin, and let's say 6. Okay, right? And it, oh no, I was mistaken. It comes the other way around. Let's see why. Okay, let's quickly see why. Okay, so mod 2, which is the 0. Okay, yeah, and mod 2, it's which will be 0. 0 will go in front of. Oh, okay, yeah. So it does come in the reverse order. So the 0 does not go in front of the empty list immediately, but 0 will go in front of whatever this returns, and this one will return the 1 1 for the 3. Okay, right, and so on. So it does come in the reverse order. Yep. I'm glad we did that. Okay, sometimes it's confusing, but I think we had seen this before too. When you cons, you sort of start getting reverse order, and that's why some of you in one of the homeworks you might have actually taken this and added the plus plus on the right side to get it in the right order. Okay, now we can do that here as well if you want, but it's not very critical because we have the ability to reverse everything later on. Okay, and finally, this is the function bools1, which generates all possible substitutions. Okay, and it's done with these 4 helper names or expressions. Okay, range is the list of numbers 0 to 2 to the n minus 1, and those each one of those numbers would correspond to one of the substitutions. Okay, and convert 0 will give false, and convert 1 will give true. So these are some simple expressions. And make n bs, what it does is that it takes the bit pattern generated by the into bin and pads it with zeros. Okay, because when you take any of these numbers and convert it to binary, they may not come of uniform length, right? They can be of different length, so we want to make them uniform, and that's why we take n. So I guess we make it into n bits. Okay, and then repeat 0, which gives you a whole bunch of zeros, are added at the end of this the bit stream. Okay. Anyway, I think we discussed this. You take n, okay, bulls, bulls 1 of n, where n is the number of variables in your formula. Okay, what it does is that it takes the range, which is 0 to the n minus 0 up to 2 to the n minus 1, which will be a bunch of numbers. Okay, and you can see that the n is required as a parameter to range. Okay, correct. Here you can see that this 2 to the n minus 1, so that's where this n will get passed. Okay, because we are using the same variable both here in this make n, but also in the where clause. Okay, so the where clause has access to the variable which is the parameter there. Okay, so, and actually within the where clause also we have the same n used here. So that variable n is obviously available in the body of this function. Okay, so we do the 0 to 2 to the n minus 1 here, a list of numbers, and then we map this on each one of those. Okay, and what this composition does is that it takes each number from the range and converts it to binary, and make n, what it does is that it pads it with 0 so that you get n bits. Okay, and the reason we need n bits is because the number of substitutions would be or the number of variables is n, and we need to provide those many trues and false values. Okay, so that's what make n will make sure that we have enough trues and falses in each one of those, and then map on that individual zeros and ones. Okay, because into bin will give you a list of zeros and ones, and this will pad zeros to it, and then what this does is that converts individual zeros and ones to trues and falses. Okay, and then this one reverses it because again, it's not really needed, but if you want them in false false in the beginning and true true at the end, then that reverses what you do. Okay, all right, so we did this and we saw some examples of that. Okay, now let's look at this another way to do this, and a much more elegant way. Okay, much more elegant way, a recursive solution. Now this guy was not recursive. Okay, so this is how you would code this in Python or something like that. Okay, even though this is functional, but we are using a lot of maps and reverses and so on and so forth, ranges. So I mean, the into bin is recursive, but the bools one is not. Okay, so the bools one's solution here is a little bit more imperative in quotes in nature. It's not imperative because it is functional, pure functional, pure function. Okay, but it tells you that, oh, you start with the list of these numbers, then convert into binary, then pad the zeros, then convert it to trues and false, then reverse it, okay, and so on. So that's what. So in some sense, there's some sequence of steps here, okay. But let's look at the simple recursive definition of bools, okay. Fantastic. It's just one line with a where clause here, okay, and this does exactly the same job as this one here, okay. I think for this I have a small example laid out here, okay, but let's look at the definition. So the bools, we just call it bools. Here we call it bools 1. I guess we could have called it bools 2, but that's okay. Bools, it takes the number n, which is the number of variables in your propositional formula, and it generates a list of bools, which is what bools 1 also did, which is all the substitutions, okay. And obviously, if n was 0, so this is going to be recursive. If n is 0, then there's no variable, so we will generate a list of the empty list, okay. I think you might be tempted to just put empty list, but you'll see later on that that won't be correct, okay. List, so this is a little bit thought you need to put in, and I think when we look at the example, you'll see why that is necessary, okay. And then the more general case would be, what you do is you do the recursive call on n minus 1, okay. Basically, if you want all the substitutions with 4 variables, okay, a, b, c, d, okay, then you do it with 3 variables, okay, and recursively. So you'll get all the substitutions for the 3 variables, okay. So let's take an example, n equals 4 and 1 less than that, which will be 3, okay. So with a recursive call, you would get all substitutions for a, b, or let's say b, c, and d, okay. It doesn't matter which 3, but let's say b, c, and d, okay. So you'll get 8 substitutions there, right? True, 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 or start with false, 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 true, and so on, okay. You'd get that, okay. So you got 8 substitutions. Now, the way to generalize this to 4 variables is to add the value of false for a, which is a left out variable, to all of these 8, and then add a value of true to all of these 8, and that's how you get that 16, okay. That's how you because these 8 patterns, and actually you might have noticed this also when you write the truth table for 3 variables, let's say 8 rows, okay. You'll see a pattern inside that, okay. The first 4 and the last 4 are differing only, especially if you write it in a sequential manner in a particular order. The first 4 and the last 4 differ only in the first variable, okay. In the first 4, the first variable is false, and the next 4, the first variable is true, whereas the rest of the values in the first 4 are exactly same as the ones in the second 4, okay. This pattern you should have observed by now, okay. This is very basics computer science 101 type of topic here, okay, on how binary number patterns are written, okay, or even booleans, okay. Anyway, so this bools n minus 1 will give you the solutions again magically, 90% sale, I always say in the class, okay. Bools n minus 1, it will give you an answer for substitutions for 3 variables, okay. Got it? And all we do is we need to attach false in front of each substitutions inside the BSS, which BSS is the 3 variable substitutions, okay. So each substitution we want to attach a false in front of it, and how do you do that? Well, it's a false colon, because colon is the cons operator, and each substitution is a list of booleans, right? So the false will get attached to each one of those, and then another map, okay, with a map false colon to each of the substitutions BSS will get the 4 valued or whatever the n valued substitutions, okay, with the false for the left out variable, okay. And the next one will be do the same thing for the true value, and then you just do the plus plus, which is combining all the substitutions in this part and that part, and you'll get the final answer. Looks very elegant, okay, very simplistic idea, but it's a recursive solution. But the key is this guy here on the base case, okay. So let's look at a quick example of this. I guess it's here, okay. I thought I needed it there, okay. Yeah, I did copy it here, so I don't need that, okay. So here it is, okay. So here is a bools 2, okay. Now Just for n equals 2 I did. So because n equals 3 gets too big, so I just did it for n equals 2. Okay. So now what is Boole's 2? It is map of false colon on Boole's 1 plus plus. I guess this can be, oops, okay, yeah. This in one line makes a little bit better. Okay. Map of false of Boole's 1, okay, plus plus map of true cons. Okay, this is not false. Okay, this is false cons. Okay, uh, and this is actually a section. Remember chapter 6 or 7 we studied sections. The cons operator takes two parameters, okay, an item and a list, right? And here we took one of the parameters, the first one, and put it in the front of the colon, and we got false colon, which becomes a section, and we apply this section to the Boole's 1, okay. Uh, Actually, not to Boole's 1, but to each item of Boole's 1 because of the map, okay. And same thing here, map through that, okay. So this is basically from this equation, okay. That equation I just expanded it out, okay. BSS is just the Boole's n minus 1, okay. All right, so that's the equation. Now this one we can work on Boole's 1 now, okay. Boole's 1, these two Boole's 1. So I'm just substituting Boole's 1 by this guy here. This whole thing is Boole's 1, which is map of false of Boole's 0 plus plus maps of true colon of Boole's 0, okay. And because we had Boole's 1 two places, I copied that here, okay. This time I went to two lines because I wanted them to line up, okay. And then now we know Boole's 0 is what we need to substitute. So we need to substitute in these four places the Boole's 0, and Boole's 0 is a list of empty list, okay. So that's what I do here, okay. So this I just substituted Boole 0 by list of empty list, and those four places, okay. So here there's nothing much has happened, okay. Now we unwind these expressions, and inside out is better. So let's look at map of false of this guy, okay. So what this will do, now you can see why we need the list of empty list here, okay, because eventually we'll get a map of false colon, which is a section, okay, map of false colon on this list. And map, what does map do? It applies the false colon section to each element in this list, and in this case that's why we need a list of lists, so that this map of false colon can apply to this empty list, okay. But if we just said list there, then there will be no element inside that, and the false will never be attached to anything, okay. So that you may want to think about it, and this is the correct way, okay. So what this will do is it'll take that empty list and put a false into it, okay. And what this guy will do is it'll take that empty list and put a true into it, and this will take the empty list and put a false into it, and this will take the empty list and put a true into it, okay. So when you do those four values, you'll get this, okay. That's a false got into that, and false got into this empty list, and true got into that empty list, and true got into empty list, okay. Now I guess this became shorter, so maybe I can put it like this, okay. So I'm trying to see. Okay, now we have to do map false on this list, okay. What is that list? That actually I should have expanded. It is false comma true, right? So I guess we needed one more line here, okay. Like, that's good. I'm glad that I'm fixing the slides as we are going, okay. So this guy would be map false of, and this is a parenthesized expression which ends here, okay. That expression, and that expression is just concatenating these two lists. So I would get, and then I can get rid of the parenthesis after the concatenation, and this will become false okay. So we'll get that, okay. So we'll get a list of two substitutions. One contains false and one contains true, okay. And then we're going to do map of false on that, okay. And I think the same thing on the second side. So this will be a plus plus plus, and I think I can copy this guy and change this to true, and that would be the expression on the second side, on this side here, okay. That is, we are mapping true colon on, so I just combine these two into that, okay. So now what we have is that we have two expressions which we need to concatenate, and the first one is mapping false colon onto this list, which is a list of substitutions of one variable, okay. right? So it'll attach false in front of this false, it'll attach false in front of this true, and this one will attach true in front of that false, and true in front of that true. And now you can see how we are getting the, so that's what we get here. Let me again bring this like that, okay? So it attaches the false in front of the false, false in front of the true, true in front of the front. And then when you add all of these four, actually, yeah, that's right, concatenate all of these four, you'll get the four substitutions which we are looking for, okay? You could try this for 3, bools 3, but don't try it for 4, 5, 6, and so on. It's very cumbersome, right? But you get the idea, okay? All right, so we have two different ways to generate all the substitutions. One which is a little bit more traditional way, some of you might prefer that. One which is a little bit more non-traditional way, in the sense that it's a very purely recursive solution, which seems intuitive and simple enough when you actually look at it and understand it. Okay, so I do want all of you to get used to both these types of solutions. Okay, both. Okay, you want to be on top of and be an expert on writing recursive solutions, and then unwinding the recursions and making it non-recursive, but also keeping it functional by composing smaller functions and so on. Okay, all right, so I think we are getting close to wrapping this tautology checker. Remember, there were duplicates in the variables, right? There was one which found the variables. There was a function called vars, which took a prop value and returned the list of variables, but may have duplicates. And I think we have seen this before. Remove duplicates. Empty list will be empty list, and non-empty list x colon xs would be x, keep the x, and then filter not equal to x on remove duplicates of xs. I think we have seen this before, so I'm going to skip that. Okay, and the final thing we need is to generate the substitutions themselves, right? Given a proposition, of course, we wrote the this function here, bools, but we're going to use the bools to generate the substitutions given a proposition, okay? Because this bools took a number n, which is the number of variables, okay? So we need to generate the number of variables, so that's what this substitutions does, okay? Given a prop, it returns a list of substitutions, okay? So P is a prop, okay? And what we do is we take the VS, which is the vars of P, and remove duplicates. Okay, so that basically do the vars, get all the variables with the duplicates, and remove the duplicates. So VS would contain all the unique variables. Okay, like ABC or something like that, or AB. Then what you do is you take the length of the unique variables VS and call bools function. Okay, there you go, that one there. Okay. And what we want to do is, because the substitutions just contain values true, false, true, comma, false, comma, so on, what we want to do here is we want to attach, let's say this example here, this is what the bools will return, right? So we want to, and this would be for the case when we had two variables, A and B, right? So we would have to assign A false and B false in this substitution, okay? And A false and B true in this substitution, and A false and A true and B false here, and A true and B true there. Okay, so we need to associate the variables with these values. Okay, and that's what this does. Okay, so bools would give you those kind of values. Okay, which is all possible values of trues and falses. Okay, all possible for the number of variables we have. Okay, and then what we do is we take the VS, which is the unique variables AB or ABC or whatever it is. Okay, and apply zip of VS, which is zip of the unique variables with each one of these. Okay, so I want to zip this guy with the variables. Okay, the variables are A and B, and good news is that the VS, the number of variables in VS would be exactly same as the number of true falses in each item of this list. Why? Because we provide the length of the VS here as an input to bools. Okay. So the zip will be a perfect match, and it will automatically associate A with false, B with false, A with false, B with true, and so on. Okay, so because we are doing a map, so that will take each variables and zip it with each one of these guys. Okay, so here's an example: substitutions of P1, which is the first formula, and we get A because that formula had only one variable, so we had only two substitutions, false and true, and then the A is attached to both of them. P2 had two variables, A and B, And you can see when I say substitutions, it generates the substitutions A for false, B for false, A for false, B for true, A by true and B by false, and A by true and B by true. So it generates all possible values for each of the variables. Okay, and that's exactly what substitutions is. And now finally we just need to check the tautology, right? So now you can see that it's pretty straightforward. It's a simple for comprehension and an and on top of it. Okay, the reason and is because we want true for all substitutions. Okay, so what you do is you get S from the substitutions of P. So S will be each one of these guys. Okay, so S will be this guy first, then S will be this guy, and so on. Okay, so S is each one of these, and what you do is you eval P given the substitution S. Okay, and that will return as a true or false. Remember, this is one of the earlier functions we learned. So this will get return true or false, and then when you put and here, that this whole thing is true only when all values of eval sp are true. Okay, right? True and is true if only all ands of all values which are anding must be true. Okay, and that's what the is tautology is. Okay, and here you go. Is tautology of p1, p2, p3, p4 is false, true, false, true. Okay, you can verify this with your discrete math truth tables. Okay. That's an interesting, I think, assignment. Now, obviously, this is a fantastic, simple enough program, but this is one of those programs which is NP complete. I don't know if you've heard the term, but it is its runtime is exponential. Okay, why? Because there are exponential substitutions. Okay, if n was 100, then you have to do 2 to the power 100 substitutions. Okay, it'll take forever. Okay. Okay, even 2 to the power 20 or 30 will take too long. So don't try. And also, it's difficult to write formulas with 20 variables and so on, right? But it is an exponential algorithm what we have done. Okay, and actually, there's no way, because it's NP complete. There's no way to nobody has discovered a polynomial algorithm for this. Okay, to check for tautology, because there's no choice but to go through all the possible substitutions and verify that it's true then. Okay, all right. We have one last example. This one is actually sort of interesting, but I don't know. I think let's go through this. It's an interesting in one way, but not so interesting in another way. Okay. Okay. Abstract machine. So what this does is that now we have another example of a data declaration. Data expression equals val int and add expression. Okay. So what this does is that it allows you to write expressions, arithmetic expressions which involve addition. Okay, that's all, nothing else, and also involves integers. So like 2 plus 3 plus 4 kind of thing. Okay, 2 plus 3 plus 4, or 9 plus 2 plus 3, like those kind of expressions. Okay, so val int is the syntax or the value or the constructor which allows you to just write a number. Okay, so instead of writing 2, you have to say val 2. Okay, and then if you want to add 2 expressions, you can say add expression. Now this might remind you of the WAE expressions which we discussed in the early part of this class. Okay, and actually it is the same. Okay, except that we are not allowing all 4 arithmetic operations, but we are just allowing add here and just a val int here. Okay, and here's a function called value, which takes an expression, which is an expression made out of these 2 types of constructors. Okay, and notice the second one is a recursive one, so that's why this can be nested deeply. Okay, and what this value function does is that it takes an expression and returns the actual value for that. Okay, so it actually adds the numbers up. Okay, and the function is pretty straightforward. If it's val n, so n must be an integer, then the answer is n. Okay, and if it is add xy, then you recursively get the value of x, recursively get the value of y through these 2 recursive calls, and then add the value. Use the Haskell plus to add those values. Okay, so here's a valid term or a value of expression. Add of val 2 and val 3. So this is actually 2 plus 3 in parentheses, and then plus 4 after that. Okay, so that's really what this is. Now, if you want, this is in math, regular math, it will look like this particular expression would be 2 plus 3 plus 4, like that. Oops. Plus 4. Okay, so that's really what this is. Okay, 2 plus 3 first, and then the plus 4. Okay, and value of E1 would be 5 plus 4, 9, right? So it's pretty straightforward. And this is how it'll unwind the recursion and do that. So I'm going to skip that, okay? Because the point of this abstract machine is not this, but it's the next idea, okay? And okay, but when you look at this, there is no guarantee the order in which Haskell will do the additions, okay? Even though it seems like it should be doing 2 plus 3 because of this parenthesis here and the plus 4 there, okay? But Haskell has its own way, okay? It chooses its own order, okay? All right? Uh, uh, I think this might be a little bit counterintuitive. Why? But uh, I think the reason is that the Haskell can parallelize. Okay, so it can actually invoke a parallel computation on the different processors it may have, and so on and so forth. Okay, even though it seems like we are the programmer is enforcing. I guess I think yeah. Even when the Haskell determines that this 2 plus 3 must be done first and then the plus 4, but in this example, since we have only the add, it really doesn't matter, right? So this plus 4 can happen actually in this case, but this is a smaller example. But in general, you can have a long expression of operations here, and there could be two different parts which can be done in parallel. Okay, one part can be computed in one core, another part can be computed in another core. Okay. Um, so this actually is in that sense, it's sort of a contrived example, but it's an interesting example where you can control the order. The programmer can control the order in which you want to do the calculations. Okay. Anyway, so the point here is that the value, the way we have defined it here, okay, uh, Haskell can override some of the orders in this because it wants to parallelize. Okay. All right. So uh, if you want to enforce some other order, you can actually modify the program and build your own evaluator code function, okay, which will evaluate in the order in which you want to. And that's what this example is about. Okay, so what we're going to do is it's a pretty small, not very much here, just a tiny example. What we're going to do is we're going to define our own control stack. Okay. All right, control stack. It's just a stack, and you want to maintain. Oops, what happened here? Maybe I didn't run this cell. Okay. Okay. We're going to define a control stack in which we are going to put our own operations, and we're going to do certain manipulations with that stack, and 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 do our own ordering of evaluations here. Okay. All right. Of expressions of this type, EXPR. Okay. All right. So we have we will define two operations. Okay, data op equals. So this is our operation. Okay, it's nothing to do with that plus there, but this is just an idea uh, as follows. Okay, so we'll define two operations, and actually. If you had more arithmetic operations like plus, minus, multiply, divide, then you can introduce more of these types. Okay, in this example, we have only one, so we say add. Now this is add capital. This is just our own notation. Okay, add int. Okay, what this does is that it'll be an operation which goes to the top of the stack, and when it's time to execute this, then it'll take and there'll be an int value next to it. Okay, what it'll do is it'll take this int value and add it to the current expression which is being evaluated. Okay, that's how this will execute. Okay, and what this does is that it just postpones evaluation of expr by putting eval expr on the stack, so that when it's time to actually calculate its value, we will bring it out from the stack and execute or evaluate it. Okay, so by doing having these two types of operations, what we have is that we have the ability now of taking an expression like this and postponing its calculation by just dumping it on top of the stack. Okay, or same thing with that if you want to do that. Okay, and also we can decide based on which order we want to do is invoke the actual addition which happens. Okay, so if you want to do this first and this later, then we can actually pop something from the stack which has add on top of it, and then so what we are really trying to do here is, now this is not the only way, there are many different ways you can code this, but we're showing you the ability of maintaining a user-defined stack of certain user-defined operations. And in this case, there are two operations. One is evaluating an expression, postponing, basically eval an expression and putting it on top of the stack basically means, oh, I'm going to postpone it right now. I'm not going to evaluate expression at this point. I don't feel like at this point, okay? And later on when I pop something from the stack and if it happens to be eval, then I will evaluate at that time, kind of thing, you see? And also postponing the actual addition by putting it on top of stack before actually I can actually perform the addition, because addition requires two integers, and this one just pushes one of the integers along with this add keyword to the stack, or constructor in this case, okay? So just gives you some idea of how you can control as a programmer, okay? This is not the only way what we are doing. There could be different ways, okay? So anyway, once we know once we have defined this data op, and then we say control stack, cont, is actually a list of ops. So that's a stack, and the first item will be the top item, the last item will be the bottom item, okay? All right. And the eval and add meanings I have sort of explained to you already, but they're also explained here. Basically, eval means that postpone, evaluating the expression, this expression. And add means that, okay, you're ready to add this integer to the current value, okay, which you get by evaluating another expression maybe, okay. So that's the meaning of those, okay. Now, here's a final solution, okay. And what we do is we define two mutually recursive solution functions. Okay, one is called eval and one is called exec. Okay, what does eval do? Eval takes an expression which is of type expr. Okay, which is what we are trying to evaluate, and evaluates it in the context of a stack. Okay, so assuming there's a stack, so this eval will basically look at the top of the stack and see what's going on there. Okay, and that might indicate what it needs to do. Okay, so we will see that, and then let's look at what exec takes. Exec, what it does is that it executes the operations on the stack with respect to an integer which has already been evaluated. Okay, and it's already become a number. Okay, maybe one of the two expressions has become a number, and then the other expression it can evaluate and add it to this guy. Okay, so that's really what these two functions are. Okay, and the body of these functions are pretty straightforward. The eval takes an expression, which is really what we want to evaluate, and a stack. Okay, and returns an integer which is the final answer. Okay. And because expression can be of two types, val n and add xy, we have these two cases, val n, and of course the second is the stack, this guy here, okay? The second parameter to eval is the stack. So if it's val n, then what we want to do is, because we have reached a leaf level on the expression parse tree, right, or the expression tree. Val n is a leaf type of value, right? Then what you do is we call this helper function, or this mutually recursive function, exec. Okay, what we say is, okay, the value of this val n is n, right? Val n is n, obviously, and then I want to execute the stack. And on the stack, I have pushed something. Okay, and pushing something happens here in this and also in this one. Okay. We'll see. Okay, so no matter what operations there are on the stack, and the stack can have only one of these two operations. Okay, we will perform the actions on the stack with this number. Okay, because this number is already n, which is already finally evaluated. Okay, now if it was add xy, that's the other case. Okay, with the stack, then what we do is we are going to postpone the y's evaluation, because that's our choice here. Okay, we could have postponed x's evaluation and gone to y. Okay, so that's where you get, the programmer gets the control on which order you want to do. Okay, so here we are doing left first and then right. Okay, but you could do right first and left and then evaluate right. So you could say eval y by pushing eval x on the stack. Okay, so that's what, when you get add expression, which is got x and y, where x and y both are expressions, which we don't know how big they are, we are choosing to evaluate the x. So we call eval of x by adding eval y on top of the stack. Okay, and maintaining that one. Okay, so this gives us some control on which order. Okay, so here we are choosing left over right. Okay, but you could have done right over left. Okay, and of course, if you had more operations in addition to add, you had subtract, multiply, divide, then you could even control in more granularity. Oh, when there are adds, will go left to right, or when there multiply, will go right to left, and that kind of thing. Okay, so we could, with our exponentiation, you can do right to left, and so on. So you can see that when you had more variety of operations here, the programmer has much more control over how, in which order they want to evaluate. Okay. Anyway, we're choosing x here, so that's why this is eval x, and then we postpone evaluation of y on top of the stack. Okay, when we push it on top of the stack means when stack executes by this exec, it will evaluate that. Okay, so basically stack is a place where we just temporarily dump something, and when exec takes over, it will take items from the top of the stack and then execute them. Okay, so you understood this, right? Eval. So anyway, the expression is given. If expression is an integer value, then it's time to go execute the stack operations. Okay. Otherwise, just put eval y on the stack. Why? Because we are choosing left first and then right. Okay. But you could have done the other way around if you wanted to. Basically, postpone it until x is evaluated. That's why eval x and then put eval y on top of the stack. Okay. And exec, what it does is it takes a stack. Okay. It's called here. Okay. These are mutually recursive. Okay, it's called there. When we reach the leaf level on the expression, we call the exec. Okay, and what this does, it takes a stack and takes an integer as a context. Remember, we provide an integer next to it when we call exec. Okay, and returns the final answer. Okay, and obviously when the stack becomes empty, that means there are no more operations to execute, and then this n will become the final answer. Okay, and that's what that is. Okay. But now we need to see what happens if the stack is not empty, and we have two possibilities on top of the stack, correct? Because we've been pushing only two things on top of the stack. One is called eval y here, and the second one is going to be pushed here, okay, in the eval y, okay? So let's see what happens when it's time to execute eval y, okay? Then what we do, and the context is n, okay? The context is n. So this n is the other value which is provided as parameter to the exec. Okay. So what we do is we say, because this n is the cumulative add, so we'll have to because eval y might take some time to because y itself might be a complicated expression. So eval y might take some while to actually evaluate to a number. So that's why we had to postpone adding n to that, okay, because we would not know the value. So that's why we add n on top of the stack using the second operation, okay, and then we this becomes a new stack, and then we evaluate this y. We call eval. So this is the mutual recursive call going back to that. Okay, very intricate connection between these two functions. Each of them calls each other. One of them has a stack as the second parameter. The other one has an integer as the second parameter. Okay. And here are the explanations. When no more operations on stack, return n. If top of stack is eval y, then call eval y with add n push to stack. And if top of stack is add n, then the two operands are ready to be added. Oh, I didn't talk about this. Suppose the top is add n, what happens? Okay, and this is the m. Oh, now we are ready, because this m would be the value of eval y, I mean some other eval y some point. At this point we are adding n. Okay, add n was added here, right? Because this n will be added. Remember, we postponed adding n to this because we had to evaluate y. Okay, so when you see add n and then this m, you will execute this operation by doing n plus m. Okay, and that becomes the new value of the second parameter for exec. Okay, and then you do that. Okay, very interesting way to do this. Okay, this small example because we have only one operation, but this gives the ability for the user to control the order in which certain operations execute in these kind of expressions. Okay, I don't know whether it's going to be used, but this gives you idea of mutually helping functions. Okay, all right, but in general what this does is, because we chose left first over right, eval proceeds downwards the parse tree to the leftmost integer in the expression, maintaining a trail of pending right hand operations on the stack. Okay, and exec what it does is proceeds upwards through the trail, because it is looking at the stack. Okay, bottom up, right? not bottom up, excuse me, last in first out. Okay, so it is processing items from the top of the stack. So it's sort of proceeding upwards the trail of all the operations we pushed on the stack. Okay, and then anytime it needs to evaluate something, it transfers controls to eval, and then when it needs to add, it performs the additions, necessary additions. Okay, all right. And then finally, we need to write one function called value, or we call it value1, which takes the expression and gives the final answer. And all it does is it calls eval, this eval, okay, with e, and then it gives an empty stack to begin with. Okay, and then you can see that value1 on e1 gives you the 9, and you can actually follow through the trace here of the items being added to the stack and so on and so forth. This is a relatively smaller example, so you can actually trace this by hand. I would strongly encourage you to trace it, and it will show you that we'll actually do 2 plus 3 first to get the 5. You can see that here. Okay, it takes a while until you reach the 5. Okay, it takes 4 or 5 steps before you get to the 5, because things are getting pushed and popped on the stack until you reach the leaf levels of the expression, and eventually you get the 5, or you get the here 2 plus 3. See, val 3 and then add 2, that would give you the 2 plus 3 equals 5. Okay, oh, actually, yeah, val 3 will put the add 2 and the 3, put the 3 there, and at this point the 2 plus 3 will become the 5, which is the n plus m there. Okay, and then the 4 will add 5 will be here, and the 4 will go to the right hand side, and then 5 plus 4 will give you the 9. Okay, so this one shows you an ability for the programmer to control operations and order of operations, which might be different than what the grammar or the expression. And also because Haskell has the ability to do parallel processing. Okay, because of the pure nature of functions, Haskell has the ability, and actually quite readily decides its own parallelization. Okay, so especially if you had a long big expression tree, it will send multiple trees, multiple subtrees to the different processors or the cores and execute them at the same time. Okay, and we know that is possible because of the pure nature of functions and so on. It won't give you incorrect answers. Okay, all right, that concludes this chapter, and also concludes the first 8 chapters of the fantastic book by Graham Hutton, Functional Programming with Haskell. Okay, and that's all we are going to cover in this set of videos. Okay, thank you, and see you around.